Welcome back. Yesterday we proved the elementary renewal theorem, which involved characterizing m of t, which is the expectation of n of t, right. We wrote down the renewal equation, which is this: m of t is equal to f x of t plus integral 0 to t m of t minus x d f x of x. This is called the renewal equation, and you take Laplace transform, you get Lm of s is equal to Lx of s over s times 1 minus Lx of s, all right. So, here Lx of s is just the Laplace transform of the underlying distribution x. So, this is e power minus s x dfx of x, and Lm is the Laplace transform of m of tau, all right. Lx of s is known to us because the renewal process inter-renewal distribution is given, right. So, you can calculate Lx of s, and you can put this in, put Lx of s into this equation to get Lm of s, and you can invert back to get m of t. Now, let us just do an example. Let fx of x is equal to half e to the minus x plus e to the minus 2 x for x greater than or equal to 0. So, this is my distribution. Okay. So, my renewal process has inter-arrival distribution given by this PDF. Okay. So, you can verify that this is a valid PDF and all that. Okay. For this you can calculate Lx of s, right. Lx of s is simply what is the transform of. So, if you have s plus 1, sorry 1 over 2 s plus 1, is not it correct, plus what happens here 1 over s plus 2, correct. So, this will just work out to 3 over 2 s plus 2 over, okay, and this is for real part of s bigger than minus 1, is not it. So, now you plug this into Lm of s, you get Lm of s is equal to you use that equation, right. You get 3.2 s plus 2 over s square times s plus 3 over 2. Okay. So, this is just an exercise in putting this Lx and manipulating. Okay. So, now we have to invert back. So, this is the Laplace transform of m of t, right. How do you invert this? Yes, you put it into partial fractions, right. So, you have to write this as in this case you have to write it as a over s plus 3 over 2 plus b over s plus c over s square, find a b c, right, correct. So, you have just two poles, right. You have origin, there is a double pole, and minus 3 over 2 there is a pole, right. So, you have to write this as some 1 over a over s plus 3 over 2 plus b over s square plus c over s, right. So, you just work this out, it comes to plus 1 over 9 times 1 over s minus 1 over s plus 3 over 2. Okay. This is for real part of s 0. So, what is m of, you can write down what is m of t, right. So, if you have some, see if you have 1 over s, that corresponds to a constant, right, for positive t, it is like 1 for positive t. 1 over s square is t, isn't it? T for is like yeah, it's like a ramp, right. So, okay, so you know all this very well. So, this m of t will be 4 over 3 t, correct, plus 1 over 9 1 minus e to the minus that, correct. This is m of t for any t greater than 0, okay, an explicit characterization of expectation of n of t for this renewal process. Of course, even easiest sanity check is if you put f x of x is equal to e power lambda e power minus lambda x, which is Poisson process, you should get back lambda t, right. M of t should be lambda t, you can check that, that is an easier exercise than this even, okay. So, it turns out, so there is a term that goes linearly in t, there is a constant term and then there is a decaying term, that is what this looks like, right. This of course, it worked out very easily because this was a rational, I mean this distribution had a rational transform, right. This is the easiest case, I mean if Lx of s is rational transform, Lm of s will also be a rational transform. So, you can do this trick to find m of t, okay. In general this can be more complicated, this is always correct, but it may not be practically so convenient to do it, alright. And of course, you can verify elementary renewal theorem easily, you can find the expectation of x of this distribution and you know there is that linear term, right. This term will turn out to be 1 over x bar, correct, you can just verify all that, okay. Actually this is what you saw in this example is pretty standard for any rational transform. You will get a 1 over s square pole and a 1 over s pole plus other poles which are always on the left half plane, okay, which correspond to decaying terms in T. So, poles are on the left half plane, you will have decaying poles. So, if you just look at this guy, if you look at this term Lm of s, there is clearly a 1 over s term, okay. So, there is definitely at least one pole at 0, right, but there is also another pole coming from 1 minus Lx of s, because if you look at Lx of 0, what is Lx of 0? Lx of 0 is just 1, right, Lx of expectation of e power s x. So, Lx of 0 is 1. So, 1 minus Lx of 0 will be 0, right. So, there will be this term 1 minus Lx of s will contribute another pole at 0. There is already a pole at 0 coming from 1 over s and there will be another pole coming from 1 minus Lx of s always, alright. So, there is you are guaranteed to have a 1 over s square term, that is all that I am saying, which corresponds to this t sort of a behavior, right, this t term that came out, right. So, this will always come, then there will also be a 1 over s term whose residue you have to find out, okay. So, normally, so you can this you know, right. So, Lx of s basically looks like 1 minus s, so 1 minus s x bar plus s square over 2 expectation of x square dot, right. So, you put this into Lm of s will then be 1 minus s x bar plus s square upon 2 expectation of x square plus dot over you will get s times 1 minus Lx of s. So, 1 minus Lx of s will be, there will be an s square term coming out, then you will have x bar minus s over 2 expectation of x square plus dot, right. So, if you just look at the leading term of this, if you just look at this bit, right, you will get, so the 1 over s square term is clear, it will be 1 over s square x bar, okay, in the transform domain, which will in the time domain will become t upon x bar, which is very happy for us because we want mt over t to go to 1 over x bar, right. So, you will always have this situation where m of t has a leading term which looks like t over x bar, okay, and that corresponds to the 1 over s square term, right. And then there will also be a 1 over s term which is like a constant, the residue at 1 over s you have to calculate. You can either do that So, what is the 1 over s residue? So, 1 over s times what is the question, right? You will get a term that looks like this. Okay. So, if you can either work this out from the series, or you can look at it in another way, which I will tell you in a minute. You will get something like this. All right, plus left half plane poles. Let me just write it like that. The other terms will be decaying. Okay. See, all other poles of Lm of s will be on the left half plane. That is because you can in fact show this. See, 1 minus Lx of s, the absolute value of Lx of s is less than or equal to 1. You can prove that, because it is a distribution. So, 1 minus it, so this Lm of s will not have any further poles on the right half plane or on the vertical axis. It all the other poles will be on the left half plane. Okay, which means that in time they will decay. Okay, just like we had in the example. Okay. So, basically the terms that matter. So, you have a second order pole at 0, which will correspond to a residue of 1 over s square, a term corresponding to 1 over s square, and a term corresponding to 1 over s plus a whole bunch of decaying terms. This is a standard thing. And if you are wondering where this comes from, so it is clear where this 1 over x bar comes from, and if you are wondering where this comes from, okay, you can algebraically see it by getting the working out. Basically, this is the residue at, this is the 1 over s residue, right. We can calculate that either from the series or by other means, but a more straightforward way to see where this comes from is to recall the other equation which had from Wald. You know this, right, expectation of NT plus 1, I had an equation, right, expectation of, can you go look at that, equal to expectation of SNT plus 1 by x bar minus, I think I will have one more term, minus 1, that is all there is. This is from Wald. Okay. So, this will just work out to be T upon x bar plus expectation of SNT plus 1 minus T correct. What have I done? I have just added and subtracted T upon x bar. See, because T upon x bar term I am getting anyway over here, right. This is the T upon x bar term, correct, and I am trying to explain where this question mark comes from, right. This the other term 1 over s, the term corresponding to 1 over s. So, that is the same as this. So, what is this term? This is just expectation of yt, right, expectation of, this is the expectation of the residual time, the ensemble average of the residual time. We have not yet calculated that, but we have calculated the time average, and we have a strong sense that they must be equal, right, intuitively. So, I am just giving you an intuitive reason that, so this guy must be T over x bar plus this guy must asymptotically look like what, expectation of x square by 2 x bar square, there is also 1 over x bar here, right, minus 1, okay, except this relationship is only for large T, right, it is not true for all T, right, this is for large T, right. See, the time average that we worked out is equal to this, but will be equal to the ensemble average expectation of y of t for large T, okay. For T finite there will be other terms, correct. So, this is not equal. So, I can say this is approximately equal. Why am I putting approximately equal? Because there will be other decaying terms. See, this equality is exact, right, T over x bar plus expectation of all that over x bar minus 1 is correct, that is exact, but in writing this I have made some approximation. So, I am just trying to argue where this guy comes from, this blue question mark comes from, right. It is roughly coming from the expected residual time, which has this term plus some transient terms which go down to 0 exponentially fast in the case of a rational transform. Okay. So, that is the intuitive justification. Okay. So, again this equality is exact, this is not exact, okay. It is true only for large T, because I have put asymptotic expected residual life to be the expectation of residual life for finite T, which is not correct, right. You will get some transient terms in general, and this transient terms you will have to work out by looking at the left half plane poles for a rational transform. Okay. As we did, now we could explicitly get those terms, the transient terms in the example, for example, right. Okay. So, this walled digression is just to justify where this term comes from, right. Where does, so this question mark that I put, where does it come from, right, that has come from the expected residual life, okay, which is roughly like this expected x square over 2 x bar, but there are also transient terms for finite T. Okay. That is all that I am saying. So, to again get back to this Lm of s, you can transform back, right, from here you can transform back and write m of t is equal to t upon x bar plus expectation of x square over 2 x bar square minus 1 plus some epsilon t. Okay. These are terms decaying T. So, this is the transform corresponding to the inverse transform corresponding to left half plane poles. You see what I have done here, right, 1 over s square x bar inverse transform is T upon x bar, and 1 over s times this constant will just be the constant, which is this guy, plus there will be all these left half plane poles, which in the example was like 1 over s plus 3 over 2, which turned out to be some decaying term. You will have a whole bunch of decaying terms depending on the particular example you are looking at. I am just capturing it as epsilon t, that is all. These terms will go to 0. Okay. So, what I am saying is that limit t tending to infinity epsilon t will be 0. Okay. So, this is what m of t looks like. Okay. But of course, this entire analysis is valid only for this rational transforms. Okay. Otherwise, if you have like e power minus s tau or something like that in the transform, it is not rational, then a simple structure like this would not emerge, because those e power minus s terms or whatever irrational terms you have in the transform will keep coming, right. But I mean the transform of Lm of s is always valid, it is just that it will not be so easy for you to invert back and get this form, that is all. Okay. So, from here, so this is only for, I mean this whole analysis only for rational transform, right, everywhere this is, okay, this whole analysis is for that. So, here you already see that we have gotten here using the renewal equation, taking its transform and analyzing the transform, right. So, if you take mt over t, it is clear that mt over t is going to 1 over x bar, right, because this epsilon t terms are dying anyway, and you have a constant over t which will go to 0. So, elementary renewal theorem is clearly obvious from this, right. So, can be deduced. For again for rational transforms. Okay. But of course, we proved the elementary renewal theorem in full generality using a truncation argument. I am just saying that if you had a rational transform, you can, you have a very explicit characterization of expectation of NT, from which the elementary renewal theorem is a obvious corollary, but this is not a very general proof. So, this is for rational transform Lx of s. Okay. There is another very important result that actually comes from, that you can actually deduce from this equation m of t. Okay. Question: for an interval, you fix this interval t comma t plus delta, what is the expected number of renewals in this interval. Okay. So, I want to look at this, how many renewals happen in this interval t plus delta. Okay. So, this is again, this is answered by a theorem known as Blackwell's theorem. Okay, that is what I want to, that is what we are heading to. Okay. That theorem answers precisely this question. Okay. Again, for a rational transform, the answer I know, right, at least for rational transform. L x of s, I have m of t plus delta, I know m of t plus delta is simply t plus delta over x bar, you look at that term, right, t plus delta over x bar plus expectation of x square over 2 x bar square minus 1 plus epsilon t plus delta. This is the decaying term, and m of t is simply t over x bar plus the same term plus epsilon t, right. What have I done? I have just copied what I know for the m of t. M of t is just expectation of n of t, right. Therefore, this guy m of t plus delta minus m of t, which is what you want, right, is equal to what? Delta over x bar plus this constant term cancels, right, plus this epsilon t plus delta minus epsilon t, right. Anyway, this whole thing is decaying in t, correct. So, for large t, expectation of n t plus delta minus expectation of n t behaves like delta over x bar. Okay. So, this is Blackwell's theorem. Okay. This is a very important theorem. Let me put that down. Let me state the theorem first. Let n t be a renewal process with inter arrival distribution that is non-arithmetic. I will tell you what non-arithmetic is. Okay. Then for each delta greater than 0, limit t tends to infinity, is equal to delta over x bar. So, I am basically looking at m of t plus delta minus m of t, which is the expected number of renewals between t and t and t plus delta, right. So, I derived all this, right. If you look at this equation, this guy, and send t to infinity, I will get delta over x bar, right. That is all I am saying, but I am saying this as a theorem for non arithmetic distributions. Okay. First of all, I have not told you what an arithmetic distribution is, and the second thing is that does this derivation above the statement of the theorem actually prove the theorem? Is it a proof of the theorem or no? It is not a proof of the theorem, right, because it holds only for rational transforms, and it turns out that rational transform, once you have a rational transform, the distribution will always be non arithmetic. Okay. Okay. So, the above derivation is sort of an appetizer, I mean it sort of tells you why the theorem is true, okay, but it is not a proof of the theorem, and in fact Blackwell's theorem proof is very non trivial. Okay. We will not do the full proof, okay, it is not a good use of class time. Actually even Gallagher omits the proof, okay, and he cites Feller volume 2 for the proof. If I remember correctly, the proof takes a slightly circuitous approach. You have to start with it uses renewal equation, and you start with fx, the CDF, which is first for prove it for simple random variables. If you remember what simple random variables are from your probability course, then you generalize, okay, but I will not do that, but I will tell you what a non arithmetic distribution is. See, I am looking at some t plus delta, right. Delta, I mean it does not have to be small, okay, this is true for any delta greater than 0, but you are looking at some t and t plus delta, right. Now, suppose I have a renewal process in which the interarrival distributions, let us say, are always integers. Renewal occurs at some integer, let us say 1 or 2 or 3 or something like that, okay. If your interarrival, for example, if your interarrival distribution takes only integer values, then all your subsequent renewals will take place at integer times, correct. So, if your interval t plus delta does not include integer, if it does not include an integer point, then for that renewal process which renews only at integer times, then expectation of n t plus delta minus n of t will be 0, right. So, clearly Blackwell's theorem cannot hold in full generality, correct. So, an example of an arithmetic distribution is what I just gave you, right. Only I mean it only renews at multiples of integers, okay. A non arithmetic distribution is basically the opposite of an arithmetic distribution. Now, what is an arithmetic distribution, right? An arithmetic distribution is corresponds to a random variable which takes values non negative, I mean with non negative probability, which are just some multiples of some parameter kappa, okay. So, renewals will happen at kappa or integer multiples of kappa, okay. That kind of a situation Blackwell's theorem cannot hold, because what if this t plus delta does not have a multiple of kappa in it, correct. So, what is an arithmetic distribution? Answer: interrenewal times take values that are integer multiples of some parameter kappa greater than 0, okay. So, it will be like xi will be kappa with parameter with probability p1 equal to 2 kappa with probability p2 dot, right. It should have only it will take values only kappa 2 kappa 3 kappa etcetera for some kappa greater than 0. Kappa can be any real number, positive real number. Okay. Okay, this sort of a distribution is known as an arithmetic distribution. Okay. So, please keep in mind that arithmetic distribution is not the same as a discrete distribution. Okay. Discrete distribution can take, it is not that it takes only integer multiples of a particular kappa, right. So, if I take xi is equal to 1 with probability p and root 2 with probability 1 minus p, is that an arithmetic distribution? Not at all. It is a discrete distribution, but not an arithmetic distribution. Is that clear? So, Blackwell's theorem concerns itself with the case when the distribution is not arithmetic. If it is arithmetic, it has no chance of holding, because this t plus delta may not include a kappa multiple in it, and therefore, it falls apart, right. But if the distribution is not arithmetic, like, so even if it is like 1 and root 2 or something like that, then asymptotically the expected number of renewals in t plus delta is delta by x bar. Okay. That is what Blackwell's theorem says. Okay. There is also Blackwell's theorem for arithmetic distributions. For arithmetic distributions, what you want is that this delta should be some multiple of this kappa. Okay. So, let me talk about span. Okay. The span of an arithmetic distribution is the largest number kappa. Maybe I should call this, I am reusing kappa, right. But I suppose it will be clear, for which the above property holds. See, what do I mean by the span? See, the example I have given, so it's the xi's take values which are multiples of kappa, right. But if it takes values which are multiples of kappa, it also takes values which are multiples of kappa by 2, right. So, you basically look for the largest such kappa for which the interval times are multiples of that number, okay. Then you call that the span. Okay. So, now I will state for the arithmetic version Blackwell's theorem for arithmetic inter-renewal distribution with span kappa limit t tending to infinity m of t plus kappa minus m of t is equal to kappa over x bar. So, you are just requiring that the delta be, you are forcing the interval to include a include one of these kappa multiples. Now, the Blackwell's theorem holds. Okay. That is all that we are saying. Okay. So, this Blackwell's theorem has a nice interpretation. So, if this delta were very small, right. So, you have this t and t plus delta, right. You have this renewal process running. Now, what is the probability of actually having a renewal in this interval t plus delta? Okay. If delta is very small, okay, assume non arithmetic for now. Okay. If delta is very small, then the probability of having 2 arrivals in the interval is very small. Okay, it will be little o delta, we can ignore it, right. So, this expected number of renewals as given by Blackwell's theorem is basically the probability that you have a renewal in T t plus delta, right. So, in T t plus delta, when delta is really small, you can have either 0 renewals or 1 renewal. 0 renewals will not contribute anything to the expectation, 1 renewal will contribute something, and 2 renewals onwards has very low probability. You can say it contributes little o delta, right. So, what Blackwell is saying is that probability of, so let us say small delta, probability of having a renewal in t comma t plus delta is what, is roughly delta over x bar, sorry x bar, yeah you are right, it is lambda delta, lambda is 1 over x bar, right, lambda is the rate of the process, right, plus some little o delta terms will come, okay. But this is for large t asymptotically, okay. So, this is what Blackwell sort of implies, right, because the expectation, if you have a small interval, the expectation fully comes from that probability of that one renewal, more than 2 renewal, 2 or more renewals has very little probability, little o delta, and 0 renewals has substantial probability, but it will contribute 0 to the expectation, correct. So, this term is basically the probability of renewal in T t plus delta is essentially like expectation of n t t plus delta minus n of t, which is like lambda delta, okay, where lambda is 1 over x bar, okay. So, it is somewhat like a renewal, we are saying this is somewhat like a renewal Poisson process, right, this, but what is the key difference? Yeah, the first key difference is that this is asymptotically true, this is not true for every t. If you have large t, the probability of having a renewal in a small interval delta is lambda delta plus little o delta. The second key difference, this is very important, is that you do not have IIP, you do not have independent increment property. So, the number of renewals in T t plus delta and an adjacent interval of another width delta, they are not independent, okay, they are dependent for a renewal process in general, okay. So, a renewal process has this lambda delta plus little o delta property asymptotically. So, sort of the stationary increment process sort of a thing comes out asymptotically, but IIP does not hold, okay, for non arithmetic renewal process, okay. I will stop here.